Hello. So what we have been doing since last classes, we are trying to address some. We are trying to see some examples of analysis of statically determinate truss using method of joints. Okay, let us continue with that. Now, next, take this example. So, this is we need to now we are going to solve this truss. Okay. Now, first is we need to determine the support reactions. Okay. So, first let us see whether it is statically determinate truss or not. The number of reactions are we have is 3, here 2. Okay, let us draw the free body diagram of the entire structure first. So this is roller support. We have this is AX, and then this is BX and BY. Okay. Again, last class also I mentioned, just to save the time, I am drawing the free body diagram of the entire structure. I am showing the sub reactions on this diagram itself, but free body means it has to be free from the support, right? So when you are replacing support by forces, don't show support and their reactions together in the same diagram. Okay. Now, so number of reactions are 3. And the number of members are 1, 2, 3, 4, 5, 6, 7. Number of members are 7, and total is, and number of joints J is equal to 1, 2, 3, 4, 5 joints. So M plus R is equal to 2J. So this is statically determinate truss. Okay. Now first let us find out the support reactions. Now if we take Fy is equal to 0, okay, let's just, this is okay. On this free body diagram, if we apply the equilibrium equation, first is summation of Fy is equal to 0. This directly gives that By is equal to what are the forces you have in y direction? You have By, and then downward 3 kilonewton force. So By minus 3, 0. So By is equal to 3 kilonewton. So this is okay. Now take summation of moment. If I take moment about A is equal to 0, say summation of moment about A is equal to 0. Okay. Now what are the forces will contribute to this moment? Ax will not contribute, By will not contribute because it is the point A lies on the line of action of B. Bx will contribute, and these 3 kilonewton load will contribute. Now the forces in Bx will be this distance into Bx, and couple, clockwise couple, and then clockwise couple by this force is 3 into this distance. Okay, let us first write the distances. These distances are L, these are all L, these angles are 30 degree. So this is 2L by root 3, and this is L by root 3. Okay. Now summation of M is equal to 0. It means, let us write it here, summation of M A is equal to 0. What it gives is Bx into L by root 3, it is positive because it is clockwise, plus 3 into 2 L, that is equal to 0, and this gives Bx is equal to minus 6 is equal to minus 6 root 3 kilonewton. So this is Bx, right. Now if I take summation of fx is equal to 0. Then horizontal component are ax and bx. This gives us ax plus bx is equal to 0. See, whenever, again I am repeating, you could have done like this. You could have showed ax in this direction and bx in opposite direction. In that case, it will be ax minus bx is equal to 0. Plus, but try to avoid that, because when you draw the free body diagram, whatever sign convention you have fixed for your free body diagram, you please do that, be consistent with that. This is equal to 0. So, this directly gives that ax is equal to 6 root 3 kilonewton. So, this is the support reaction. So, we have obtained the support reactions, right. Now, let us now determine the member forces. Okay. Now, let us first draw the let us identify which joint shall we take. We cannot start with joint E, because joint E has 3 members, so 3 unknowns, equations will be only 2. We cannot start with joint C, because C has 4 members, so we have only 2 equations. We cannot start with joint A as well, because A has 3 unknowns, and equations are only available 2. So, either we can start with joint B or we can start with joint D. In both the cases, number of unknowns are 2. So, let us start with joint D. Okay. Now, what is the free body diagram of joint D? So, this is your support reaction, right. Let us draw the free body diagram of joint D. So, this force is FCD and this force is FDE, and then another force 3 kilonewton. This is D and this is FBD of D. Okay. Now, take summation of forces in x direction is equal to 0. What it gives that, or take summation of forces in y direction is equal to 0 first. Y direction is equal to 0. Then it gives y direction component as 3 kilonewton and the component of FD, this angle is 30 degree, this angle is 30 degree. Okay. So, what we have is FDE, which is the vertical component, which is downward, that is why put negative sign here, and then minus 3 is equal to 0, 3 in the minus because it is acting downward. So, this gives me FDE is equal to minus 6 kilonewton. So, FDE is obtained, right. Now, in the same equation, if we take summation of same free body diagram, take summation of Fx is equal to 0, then what we have? We have FCD minus FD cos 30 is equal to 0, right. Cos 30 is equal to 0. Okay. This is again negative. Both are negative because as per our sign convention, both are in this direction and the component of this also in this direction. But our sign convention is this direction is positive. Okay. Now, if D is already obtained 6 kilonewton, and from this equation we can get FCD is equal to 3 root 3 kilonewton. So, FCD is determined. So we have already, so this is determined, right? This is determined. Now let's see what joint. So these unknowns are, we have already obtained the member forces in these two members, Let us see now which joint to take next. Joint C, steel joint C has three unknowns. It has originally 4 unknown, but one is already computed. So but still it has 3 unknown, so we cannot next take joint C. Joint E, it was originally, it has 3 unknown, but now this is known to us, member forces in member ED. Now only unknown it has 2, member force in this and member is this. So let us draw the free body diagram of joint E. Now joint E will be the free body diagram FBD of E, right? Now FBD of E will be this and vertical component like this. All these angles are 60 degree, these angles are 60 degree, okay. This is FED, FAE and then FCE, okay. Now if we take summation of Fx is equal to 0, it gives us FAE sine 60 minus, this is plus FED sine 60 is equal to 0, and this gives me FAE is equal to FED. So forces in this member and forces in these members are same, okay. Now this member already we have determined FED is already determined minus 6 kilonewton. So this we can write FAE is equal to minus 6 kilonewton, okay. Now next what we have to take, we have to take the forces in vertical component. So vertical component will be component of this and this, and the force in member C itself. So what is, let us once again draw the free body diagram of this. It was FED and it was FAE and the force FC, this is 60 degree, this is 60 degree. If you take summation of y is equal to 0, then we get FCE is equal to 6 kilonewton, okay. This expression I'm just writing the final result because it is just the some algebraic operation. So FC is equal to 0. Now we have already, now in this case we have determined these forces, we have determined these forces, right. Now next what we can do, next we can take free body diagram of joint B to determine this force and this force, okay. Free body diagram of joint B, if I draw, BD of B, then the free body diagram will be this is, and then this horizontal reaction Bx and vertical reaction By, and this will be FBA and FBC, and this angle is 60 degree, okay. Now if I take summation of Fx is equal to 0, then it gives me what are the forces we have. Bx is positive, then plus FBC sine 60. Bx already we obtained, Bx is equal to Bx is equal to minus 6 root 3, it's the support reactions, and so if I minus 6 root 3 plus FBC root 3 by 2, this gives me FBC is equal to 12 kilonewton. Okay, so FBC is determined. It is determined. Let's calculate FAB. FAB we can calculate by applying summation of Fy is equal to 0. Right? If I take Ay is equal to 0, the equations are By plus By minus FBA and then minus component of FBC cos degree, and then if I substitute all the BC is known, By is known, only unknown is BA, and from this if I substitute all the values, BA we get is minus 3 kilonewton. Okay, you see, now this is also known, so this is now known, this is known, only thing left is this member. Okay, similarly you can draw the free body diagram of this joint and find out the forces in this member. The forces in this member will be forces in member FAC will be 5.2 kilonewton minus. Okay, so this is method of joints. Okay, so now similarly once you have all the member forces, you can draw the member force diagram of the truss. Okay, just quickly one more example. There is a specific purpose of this example. You see here, what we need to determine is the member force in member CD, right? Member CD. Okay. Now this is the problem. Suppose if because we are discussing method of joints today, suppose if I have to find out the force in member CD using method of joints. Okay, now what we have to do is, first we need to find out the support reaction. Okay, once we know this support reaction, we need to determine, we can take this joint and determine the force in this member and force in this member. Once we know the force in this member, we need to take this joint to determine force in this member and force in this member. Once we know the force in this member, we can take this joint to determine force in this member and force in this member. If you go this way also similar thing we need to do. So in order to get the member force in CD, what are the operations we need to do? We need to determine the support reactions, then one joint, free body diagram, one joint, apply equilibrium equation, second joint, apply equilibrium equation, and third joint, apply equilibrium equation. Similarly here also we need to take 2 or 3 free body diagram to find out member force in CD. Okay. Now is there any other way we can determine the forces in these members? Okay, let us see how we can determine, how we can avoid using so many free body diagram of joints to determine the force in member CD. Okay, first if I break the structure, suppose for instance for instance, suppose if I break the structure here, okay, so now I have two part in the structure, one part is this and another part is this. What will be the free body diagram of this part? If I draw the free body diagram of this part and free body diagram of this part, free body diagram of this part will be, you see, now this break line only, this line breaks only member AF and member AD, all other members are remain unaffected, right. So this is this part of the structure, okay. Now since now this member AF and AD is broken now, so that has to be represented, that it was originally continuous, that has to be represented by forces. So this force will be FA and this force will be FAD. Okay. So this is the free body diagram of this part of this structure. Similarly, I can draw the free body diagram of this part of the structure. What was this part of the structure? This part of the structure was only this AF and AD is broken. So this is A and this is the support reaction AY, AX, and then this is F and FAD. Okay. Now, what is the difference between what we have just now done and the method of joints we have discussed so far? Is in this case what we have done is we take a section from the structure, and this is the free body diagram of the section of one section. This is the free body diagram of the other part of the section. Okay. Now, instead of drawing the free body diagram of the joints and apply equilibrium equation on those free body diagram, we can also take several sections and apply the free body diagram on several sections and draw the free body diagram of those sections and apply the equilibrium equations on these sections. Okay. Now, this method is called method of section. Okay. Now, what we'll do is we'll stop here. Next class we'll start with the same problem, this problem, and then see using method of section just now, which is demonstrated here, using method of section, finding member force in CD becomes much easier. Okay. So that would be the so next class what we do is we'll discuss analysis of statically determinate truss using method of sections. We'll start with this example. We'll demonstration of the method of section. We'll start that with these examples. Okay. We'll stop here. Thank you.